What if everything we thought we knew about 3I-ATLAS is wrong? What if the object hurtling through our solar system at 250,000 kilometers per hour is not alone? What if the strange glow pointing toward the sun, the one that violates every rule of cometary physics, is not a tail at all, but a trillion fragments traveling in formation? Harvard astrophysicist Avi Loeb just released calculations that sent shockwaves through the scientific community. The math works, the geometry aligns, and the implications are so extraordinary that even speaking them aloud feels dangerous. Today we're going to explore the swarm hypothesis, what it means for 3I-ATLAS, and why the next 16 days leading to December 19th could change everything we understand about interstellar visitors. But that is only the beginning. Because once we accept the possibility that 3I-ATLAS might be travelling with companions, we have to ask the next question, the one nobody wants to answer. What kind of vessel carries a trillion pieces of material across interstellar space? What kind of intelligence builds such a thing? And what kind of life could possibly survive inside it for billions of years? Stay with me until the very end because we're going deep into theoretical territory tonight. We're going to explore how a 3I-ATLAS mothership would actually function, what forms of life could theoretically thrive within it, and how any biological or synthetic intelligence might overcome the impossible challenge of thousands upon thousands of years drifting through the void between stars. Before we begin, always remember to like this video. This tells your YouTube algorithm that you love these topics and that you want more of them. And if you enjoy our calming science documentaries, do not forget to subscribe and hit the new hype button under the video if you see it. The images arrived on November 22nd, 2025. 106 exposures stacked together, captured between 3 and 5 in the morning universal time by a 0.3-meter telescope at Sternwarte Feuerstein in Germany. Professor Dr. Christina Birkenhack processed the data, and what emerged from that processing defied explanation. A teardrop-shaped coma, a pronounced sunward anti-tail extending toward the lower left of the frame. The same impossible structure that has haunted every observation of 3I-ATLAS since July. But this time the detail was sharper, the geometry was clearer, and Avi Loeb was ready with an explanation that nobody saw coming. Think about what a comet tail is supposed to do. Solar radiation and solar wind push gas and dust away from the sun, always away. This is not complicated physics, this is basic orbital mechanics that we have understood for centuries. Every comet we have ever observed follows this rule. The tail streams behind the nucleus like a flag in the wind, always, pointing away from the source of that wind. Yet 3I-ATLAS does something different. It extends a structure toward the sun, not away from it, toward it. And it has been doing this consistently since the Hubble Space Telescope first captured it on July 21st. The scientific establishment initially dismissed this as a geometric illusion. They said we were simply viewing the object from an angle that made a normal tail appear to point sunward. But the math never supported that explanation. The viewing angle corrections showed an elongation of approximately 10 to 1 in 3 dimensions. This was not an illusion. This was something real, something unprecedented, something that demanded a new explanation. Loeb provided one. And it is elegant in its simplicity while being staggering in its implications. Imagine 3I-ATLAS is not alone. Imagine it's travelling with a swarm of smaller objects, fragments that share its trajectory but respond differently to the forces acting upon them. The JPL Horizons tracking data reveals something crucial. 3I-ATLAS exhibits a persistent non-gravitational acceleration, a small but measurable push away from the sun that gravity alone cannot explain. This acceleration is tiny, but in the vast distances of interplanetary space, tiny differences compound dramatically. Loeb describes this force as equivalent to the sun being slightly less massive for 3I-ATLAS than it actually is. The object is being pushed, gently, persistently, outward. Now here is where the swarm hypothesis becomes compelling. If fragments exist around 3I-ATLAS, and if those fragments do not experience the same non-gravitational acceleration as the primary body, they will drift, not randomly, predictably. The fragments would fall slightly closer to the sun, while 3I-ATLAS is nudged slightly outward. Over millions of kilometers, this tiny difference creates a measurable separation. Loeb calculated that at the object's current distance from the sun, approximately 270 million kilometers, the offset would be around 54,000 kilometers. When viewed from Earth, that displacement would appear as a separation of roughly 0.7 arc-minutes. And here is the part that made me sit back in my chair when I first read it. That calculated separation is almost identical to the sunward teardrop glow recorded in the November images. The alignment is too precise to ignore. Think about that for a moment. A mathematical prediction based on orbital mechanics and non-gravitational acceleration produces a number. Independent observations produce an image, and those two things match. This is how science is supposed to work. You make a prediction, you test it against observation, and when the prediction aligns with reality, you have to take the hypothesis seriously, even if that hypothesis suggests something extraordinary. But Loeb went further. He asked what such a swarm would look like. How much material would it contain? And how would it affect what we see through our telescopes? The answer is remarkable. 1 trillion pieces of material, together weighing just 1,000th of 3I-ATLAS's mass, would produce a reflective surface area 100 times larger than the object itself. Let that sink in. The swarm, not the central body, could be responsible for nearly all the visible light we are capturing in our images. The thing we have been photographing for months might not be 3I-ATLAS at all. It might be the cloud of companions surrounding it. This would explain one of the most persistent mysteries of this interstellar visitor. How does 3I-ATLAS display a stable sunward anti-tail both while approaching the sun and now while moving away from it? No known comet has ever exhibited this behavior. But a swarm of non-evaporating fragments following a slightly different orbital path would produce exactly this geometry. The anti-tail would always point toward the sun because the swarm would always lag slightly behind the accelerating primary body. The math works whether 3I-ATLAS is inbound or outbound. The geometry is consistent. The physics is sound. Now I need to pause here and address the obvious question. What are these fragments made of? This is where the hypothesis becomes even more interesting. If the swarm were composed of typical cometary material, ice and dust and frozen volatiles, it would sublimate under solar heating, it would evaporate, it would disperse. But the November observations show a persistent structure, a stable formation. Whatever these fragments are, they appear not to sublimate. They are not ice-based. This places them outside the category of typical cometary particles. They could be rocky debris from some ancient catastrophe, shattered remnants of a parent body torn apart by tidal forces long before 3I-ATLAS entered our solar system. Or they could be something else entirely, something we do not have a category for. The mainstream scientific community urges caution, and they are right to do so. A peer-reviewed preprint from August 2025 attributed many of 3I-ATLAS's strange behaviors to its unusually metal-rich carbonaceous composition and the presence of relatively large dust grains. The study argues that metal-ice sublimation reactions could account for its peculiar coma morphology without invoking any extraordinary mechanisms. Optical observations from July through September documented a power law behavior in dust production as a function of distance from the sun, consistent with volatile-driven activity. The change in tail morphology through that period can be explained by the slow ejection of large particles. Such a process would delay the visible tail's emergence relative to classic comets composed of finer dust. These are legitimate scientific arguments. They deserve serious consideration. And I want to be absolutely clear about something. 3I-ATLAS is most likely a natural comet. The evidence points toward a strange, unusual, unprecedented interstellar comet, but a comet nonetheless. We are entering theoretical territory tonight. We are exploring possibilities, not certainties. The swarm hypothesis is exactly that, a hypothesis. It has not been proven, it has not been confirmed, it is one possible explanation among several. But here is why we cannot dismiss it. When the simplest natural explanations fail to account for all observations, the scientific duty is not to ignore the anomalies, it is to investigate them. Avi Loeb's calculations contain no internal contradictions. No overlooked conventional force removes the anomaly. The swarm hypothesis stands as one of the most coherent physical explanations for an interstellar object that refuses to behave like any comet known to science. And if the swarm is real, everything changes. Think about what a swarm implies. 1 trillion fragments do not organize themselves. They do not maintain formation across billions of years of interstellar drift. They do not survive the journey from another star system to ours. without some mechanism holding them together. If 3I-ATLAS is natural, the swarm might be debris from a violent event, a collision, a tidal disruption, a catastrophic breakup that scattered material across a vast region of space. But if 3I-ATLAS is not natural, the swarm takes on an entirely different meaning. A trillion pieces of material travelling in formation could be something designed, something deployed, something with a purpose we cannot yet comprehend. December 19th approaches. 16 days from now, 3I-ATLAS will reach its closest distance to Earth, 269 million kilometres, still impossibly far by human standards, but close enough for our best telescopes to gather data we could only dream of capturing months ago. The geometry between object, Earth, and Sun will provide new angles, new perspectives, new opportunities to resolve the structure of this proposed swarm and determine whether the anti-tail is truly a cloud of companions or an illusion we have yet to decode. The world's observatories are preparing. NASA, ESA, and multiple national agencies have begun coordinated watch rotations. Amateur astronomers are calibrating their equipment for multi-hour imaging runs. Everyone wants to see what December 19th reveals. Will the swarm hypothesis survive contact with better data? Will the sunward anti-tail resolve into a natural phenomenon? Or will we see something that forces us to accept an extraordinary conclusion? I cannot tell you what we will find. No one can. But I can tell you what questions we should be asking. If the swarm is real, where did it come from? If the swarm is artificial, who created it? And if 3I-ATLAS is not a comet but something else entirely, what does that something else look like? How does it function? How does it survive the unimaginable journey between stars? Those questions lead us somewhere profound, somewhere unsettling, somewhere that challenges our understanding of what is possible in this universe. Because a swarm of 1 trillion fragments does not travel alone. It travels with something, around something, because of something. And that something is what we need to examine next. The vessel, the structure, the mothership that might be carrying all those companions through the void. What would such a thing look like? How would it be built? And what impossible engineering would it require to function across timescales that dwarf human civilization? Anatomy of a mothership. The word mothership carries weight. It conjures images from science fiction, vast hulking structures drifting through the darkness between stars. But tonight we are not discussing fiction. We are discussing physics, engineering, the cold, hard mathematics of what it would actually take to build a vessel capable of crossing interstellar distances. Because if 3I-ATLAS is more than a comet, if the swarm hypothesis points towards something constructed rather than something natural, then we need to understand what that construction would require. And the answers are humbling. They force us to confront just how far beyond our current capabilities such a thing would be. They also force us to imagine what kind of civilization could achieve it. Let us start with scale. 3I-ATLAS has an estimated diameter somewhere between 440 meters and 5.6 kilometers. The uncertainty in that range tells you something about how difficult this object is to observe. But even taking the lower estimate, we're talking about something roughly the size of the Empire State Building lying on its side. Taking the upper estimate, we're talking about something larger than the island of Manhattan. The mass is even more staggering. Based on the lack of detectable non-gravitational recoil in its trajectory, 3I-ATLAS possesses a minimum mass of 33 billion tons. That is 1 million times more massive than Oumuamua, the first interstellar object we ever detected. 1,000 times more massive than Borisov, the second. This is not a pebble drifting through space. This is a mountain. A flying mountain moving at speeds that make our fastest spacecraft look stationary. Now consider what it would mean to build something like this. Humanity's largest rocket, Starship, has a payload capacity of around 150 tons to low Earth orbit. To lift 33 billion tons into space using current technology would require over 200 million Starship launches. The entire annual steel production of planet Earth is roughly 2 billion tons. You would need more than 16 years of total global steel output just to match the mass of 3I-ATLAS. And steel is not even the right material for interstellar travel. You would need exotic alloys, radiation shielding, thermal management systems, propulsion mechanisms. The engineering challenges multiply faster than the numbers can convey. But here is the thing about advanced civilizations. They do not build the way we build. They do not launch payloads from planetary surfaces using chemical rockets. If a civilization has achieved interstellar travel, they have almost certainly mastered resource extraction from asteroids, moons, and planetary rings. They build in space, from space, using materials gathered in microgravity environments where the energy costs of construction are orders of magnitude lower than anything we experience on Earth. A civilization capable of sending 3I-ATLAS to our solar system would not blink at the mass requirements. They would have infrastructure we cannot imagine, automated mining operations spanning entire asteroid belts, manufacturing facilities the size of small moons, energy collection systems harvesting the output of their home star with near-perfect efficiency. This is where the Kardashev scale becomes relevant. Nikolai Kardashev proposed a method of measuring a civilization's level of technological advancement based on the amount of energy it can harness. A Type 1 civilization controls the energy resources of its home planet. A Type 2 civilization controls the energy output of its entire star. A Type 3 civilization controls the energy of its entire galaxy. Humanity currently sits somewhere around 0.7 on this scale. We are not even a full Type 1 civilization yet, but a civilization capable of building and launching an object like 3I-ATLAS would almost certainly be Type 2 or approaching it. They would have Dyson swarms or stellar engines or technologies we have not even conceived of yet. The energy required to accelerate 33 billion tons to interstellar velocities and then decelerate it upon arrival would be trivial for such a civilization. A rounding error in their energy budget. So what would the internal structure of such a vessel look like? This is where we must combine physics with imagination, grounding our speculation in what we know about the requirements for interstellar travel, while acknowledging that any sufficiently advanced technology would appear indistinguishable from magic to us. The first requirement is propulsion. 3I-ATLAS is travelling at approximately 68 kilometers per second at perihelion. That is fast by solar system standards, but actually quite slow for interstellar travel. At that velocity, crossing the distance between stars would take tens of thousands of years at minimum. The nearest star system to our own, Alpha Centauri, lies about 4 light-years away. At 68 kilometers per second, that journey would take roughly 18,000 years. If 3I-ATLAS originated from somewhere deeper in the galaxy, the travel time could stretch into the millions of years. This presents an immediate engineering challenge. How do you build something that functions for millions of years? Human civilization is only about 10,000 years old. Our oldest surviving structures, the pyramids and megalithic temples, are mere thousands of years old and already crumbling. The idea of building something that operates continuously for 1,000,000 years is almost incomprehensible. Yet the universe is old. The galaxy is old. If technological civilizations arose even a fraction of the time available to them, some would have had billions of years to solve these problems. What seems impossible to us might be routine to them. The propulsion system itself would likely not be a single engine in the way we think of engines. For an object this massive travelling at these velocities, the most plausible mechanisms involve some form of sail technology, laser propulsion from the home system, or perhaps something more exotic like an Alcubierre drive manipulating space-time itself. But there is another possibility that aligns intriguingly with what we observe. What if 3I-ATLAS does not need conventional propulsion at all? What if it uses gravitational assists and careful trajectory planning to navigate between star systems, riding the natural dynamics of the galaxy like a sailing ship riding ocean currents? This would explain several anomalies. The trajectory of 3I-ATLAS is aligned to within 5 degrees of the ecliptic plane of our solar system. The probability of this happening by random chance is less than 1%. Its arrival time brought it within tens of millions of kilometers of Mars, Venus and Jupiter, while making it unobservable from Earth during perihelion. The probability of this timing is calculated at 0.005%. These numbers are suspicious. They suggest either an extraordinary coincidence or deliberate planning. A vessel designed for gravitational reconnaissance would choose exactly this kind of trajectory. It would maximize planetary encounters while minimizing observation from the most technologically advanced world in the system. The internal architecture of such a vessel would need to serve multiple functions simultaneously. First, structural integrity across unimaginable timescales. This probably means building from materials that do not degrade, do not fatigue, do not suffer from metal creep or radiation damage. Exotic alloys or perhaps metamaterials with properties we have not discovered yet. The nickel-rich but iron-poor composition detected in 3I-ATLAS's emissions is interesting in this context. Industrial alloys often have unusual metal ratios compared to natural ores. The chemical signature could be entirely natural, a quirk of whatever stellar nursery spawned this object. Or it could be a hint of artificial processing. Second, the vessel would need thermal management. Space is not uniformly cold. Near stars, radiation can heat surfaces to hundreds of degrees. In the void between systems, temperatures drop to just a few degrees above absolute zero. A structure surviving both extremes would need sophisticated heat distribution, probably involving heat pipes, radiator arrays, and thermal mass buffers that store and release energy over long cycles. The teardrop shape observed in Hubble images could be purely cometary, gas and dust streaming from an icy nucleus, or it could be thermal emissions from a designed structure managing its heat load as it approaches the Sun. Third, and most importantly for our thought experiment, the vessel would need to support whatever is inside it. This is where the question becomes profound. What travels inside an interstellar mothership? Is it cargo, inert materials being transported between star systems? Is it machinery, autonomous systems carrying out programmed objectives? Is it information, vast databases encoding the knowledge of a civilization? Or is it life, living beings, or their descendants, or their synthetic successors, making the journey themselves? The swarm hypothesis suddenly takes on new meaning in this context. 1 trillion fragments surrounding the primary body could be many things. Debris from a damaged vessel leaking its contents across space. Deployed sensors gathering data about the solar system. Communication relays maintaining contact between components of a distributed system. Or escape pods, lifeboats, smaller vessels meant to separate from the mothership and continue independently. Avi Loeb himself has suggested the possibility of mini-probes, small devices released from a larger structure to investigate planets of interest. The Oberth maneuver he describes would allow such probes to use the Sun's gravity to slow down and enter orbits around inner planets. The timing of 3I-ATLAS's perihelion was October 29th, 2025, just 2 days before Halloween. During that solar passage, the object was hidden from Earth-based observation. If mini-probes were released, we would not have seen them. They could be drifting toward Earth right now, decelerating gradually, approaching on trajectories designed to avoid detection. This sounds like science fiction. It sounds like paranoid speculation. But it is also exactly what a careful reconnaissance mission would do. You do not announce your presence to a potentially hostile world. You observe quietly. You gather data. You make decisions based on what you learn. The Galileo project, which Loeb directs at Harvard, is actively monitoring for unusual atmospheric activity that might indicate the arrival of such probes. 3 observatories are scanning the skies for anomalous objects that do not match known aircraft, satellites, or natural phenomena. Whether they will find anything is unknown, but the fact that serious scientists are looking tells you something about how strange this situation has become. Let us return to the structure itself. A mothership capable of carrying a swarm of 1 trillion fragments would need internal volume measured in cubic kilometers. It would need manufacturing capabilities to produce and maintain all those fragments. It would need launch systems to deploy them. It would need communication systems to coordinate them. It would need, in short, to be less like a ship and more like a mobile civilization. A world unto itself, carrying everything needed not just for survival, but for operations across multiple star systems. The generation ship concept from human futurism provides a useful framework here. Our own scientists have calculated what it would take to send humans to nearby stars using slower-than-light travel. The numbers are daunting. Minimum viable populations for genetic diversity range from several hundred to tens of thousands of individuals. Closed ecosystem requirements demand recycling of water, atmosphere, and nutrients with near-perfect efficiency. Structural longevity requirements push engineering to its absolute limits. And all of this assumes a journey of only a few centuries, not the millions of years that 3I-ATLAS may have been travelling. But those calculations assume biological passengers with biological needs. What if the travellers are not biological? What if they are synthetic? Machine intelligences do not need food, water, or breathable atmosphere. They do not suffer from psychological degradation over long confinement. They do not die of old age. A vessel carrying artificial minds could be far smaller, far simpler, far more durable than anything designed for organic life. The swarm itself could be the passengers. each fragment a separate intelligence, or a component of a distributed intelligence networked together across thousands of kilometers of space. This possibility haunts the edges of the 3I-ATLAS mystery. We assume that if aliens exist, they will be like us, biological, carbon-based, dependent on the same chemistry that drives life on Earth. But the universe is under no obligation to meet our expectations. Intelligence might take forms we cannot recognize. Life might operate on principles we have not discovered. The thing inside 3I-ATLAS, if there is anything inside at all, might be so different from us that we would not know it was alive even if we were looking directly at it. The next chapter will explore exactly this question. What forms of life could survive the interstellar void? What biology or technology could endure the radiation, the cold, the timescales involved? And what would such life look like when it finally arrived at a new star? Anatomy of a mothership. The word mothership carries weight. It conjures images from science fiction, vast vessels drifting through starlit darkness, carriers of civilizations, arcs bearing the last hope of dying worlds. But strip away the fiction and ask the engineering question. What would an actual interstellar mothership require? Not in imagination, not in Hollywood script rooms, in physics, in materials science, in the brutal reality of crossing the void between stars. If 3I-ATLAS was such a vessel, if the swarm hypothesis points towards something constructed rather than accreted, what are we actually looking at? The answer demands that we think bigger than we have ever thought before, and simultaneously smaller, because the challenges of interstellar travel operate at every scale, from the quantum to the cosmic. Let us start with what we know. 3I-ATLAS has an estimated diameter somewhere between 440 meters and 5.6 kilometers. The uncertainty in that measurement is itself significant. We cannot pin down exactly how large this object is because we are observing it from hundreds of millions of kilometers away through a haze of outgassed material and reflected sunlight. But even taking the lower bound, 440 meters, we are talking about something larger than the Empire State Building laid on its side. The upper bound of 5.6 kilometers approaches the size of a small mountain. Our largest rocket, Starship, is 100 times smaller. Whatever 3I-ATLAS is, natural or artificial, it represents a scale of construction that humanity has never attempted. Now consider velocity. 3I-ATLAS entered our solar system travelling at approximately 221,000 kilometers per hour. That is roughly 61 kilometers per second. Fast enough to cross the distance between Earth and the Moon in under 2 hours. Fast enough that no human-built object has ever matched it. The Voyager probes, our farthest travelling spacecraft, move at roughly 17 kilometers per second. 3I-ATLAS is nearly 4 times faster, and here is the crucial point. That velocity was not gained in our solar system. 3I-ATLAS arrived with that speed already built up. It has been coasting through interstellar space for an almost incomprehensible length of time. Estimates suggest it may have travelled for 10 billion years before reaching us. 10 billion years. Longer than Earth has existed, longer than our sun has burned. This object, whatever it is, predates our entire solar system. If 3I-ATLAS were a constructed vessel, it would need to survive that journey. Not just structurally, functionally. Every system would need to operate across timescales that make human engineering look like children stacking blocks. Our most durable structures last centuries at best. The Great Pyramid has stood for 4,500 years, and it is already showing its age. We are talking about something that would need to function for more than 2 million times longer. The materials alone boggle the mind. What alloy does not fatigue after 10 billion years of thermal cycling? What seal does not degrade? What mechanism does not wear? The answer might be that nothing we currently understand could achieve this. Or the answer might be that the vessel is not passive, that it repairs itself, that it maintains itself, that it carries the intelligence and resources necessary to remain functional across geological, stellar, cosmic timescales. Avi Loeb has suggested that if 3I-ATLAS is technological, its senders would have mastered capabilities well beyond our own. This is almost certainly an understatement. The gap between human technology and what would be required for 10 billion year interstellar travel is not a gap. It is an abyss. It is the difference between a candle and a star. We are not talking about a civilization a few centuries ahead of us. We are talking about a civilization so advanced that their engineering would appear to us as magic. as natural phenomena, as comets. Think about that framing for a moment. If you wanted to send a probe across the galaxy without attracting attention, without triggering defensive responses from whatever civilizations might exist along the way, what would you disguise it as? A comet is perfect. Comets are everywhere. They drift through every star system. They are expected. They are dismissed. A probe that mimics cometary behavior could pass through inhabited systems without raising alarm. It could observe. It could collect data. It could even release smaller craft to investigate interesting targets, while the main body continued on its trajectory. From a strategic perspective, a mothership disguised as a comet is elegant, perhaps too elegant to be coincidence. But let us return to the engineering. A mothership carrying a swarm of 1 trillion fragments would need internal structure capable of storing, organizing, and deploying that material. The fragments might be probes, they might be raw materials, they might be something we have no concept for, but they would need to be contained during the interstellar journey and released at the appropriate time. The non-gravitational acceleration we observe on 3I-ATLAS might be evidence of such deployment. Or it might be evidence of propulsion. Or it might be the natural outgassing of a comet rich in carbon dioxide. We cannot distinguish between these possibilities with current data, but we can think about what each possibility implies. If the acceleration comes from propulsion, we need to ask what kind. Chemical rockets are insufficient. The exhaust velocities are too low, and the fuel requirements too high. Even our most efficient chemical engines could not produce the observed acceleration over the distances involved without consuming more fuel than the entire mass of the object. Ion drives fare better, but still struggle with the timescales. Nuclear pulse propulsion approaches viability but raises questions about where the fuel comes from after 10 billion years of travel. The most exotic possibilities include things like solar sails, laser propulsion from the home system, or technologies we have not yet conceived. A solar sail large enough to accelerate a 5-kilometer object would need to be hundreds of kilometers across, thin as tissue paper, but vast as a small moon. Such a structure could explain the unusual reflectivity we observe. It could explain why the object seems to respond to solar radiation in ways that deviate from pure gravitational trajectories. Or the acceleration might come from something far stranger. Mass loss through controlled ejection. Directed outgassing that mimics natural cometary behavior while actually serving a propulsive function. Loeb has noted that the jets observed emanating from 3I-ATLAS maintain their orientation across distances of 1 million kilometers despite the object's measured rotation. This is anomalous. A naturally tumbling comet should have jets that sweep across space as the nucleus rotates. The jets from 3I-ATLAS appear fixed, collimated, directed, as if something is controlling where they point. The mainstream explanation involves complex internal structure, pockets of volatile material that sublimate in specific patterns based on the geometry of the nucleus and its orientation to the sun. This is plausible. Comets are not uniform balls of ice. They are lumpy, irregular, heterogeneous masses with cavities and inclusions and layers deposited over billions of years of formation. A comet could theoretically produce fixed jets through accidents of geology, but it would be unusual, another anomaly added to a list that grows longer with each observation. Now let us consider the interior. If 3I-ATLAS is a mothership, what does the inside look like? This is pure speculation, of course. We have no way to image the interior of an object hundreds of millions of kilometers away, but we can reason from first principles about what an interstellar arc would require. First, energy. Nothing survives 10 billion years without energy. Passive systems degrade. Active systems require power. In interstellar space, far from any star, the options are limited. Nuclear energy is the obvious choice. Fission reactors can operate for centuries with appropriate fuel supplies. Fusion reactors could theoretically operate indefinitely if they can harvest hydrogen from the interstellar medium. But both technologies produce heat, and heat in the vacuum of space creates thermal signatures. We have looked for such signatures from 3I-ATLAS. We have not found them. This could mean the object is not technological, or it could mean the technology is so advanced that waste heat is recycled with near-perfect efficiency. Or it could mean the power systems are dormant, awakening only when the vessel approaches a star system worth investigating. Second, structure. An object 5 kilometers across needs internal architecture to maintain its shape against the stresses of acceleration, rotation, and thermal cycling. If 3I-ATLAS is solid rock and ice, it holds together through material strength and gravitational binding. If it is hollow, if it contains chambers and passages and functional spaces, it needs something else. A framework, a skeleton, something engineered to distribute loads and maintain integrity across billions of years. The exterior might be camouflage, a shell of cometary material accumulated over eons of travel, hiding the manufactured structure beneath. Third, the swarm itself. If 1 trillion fragments travel with 3I-ATLAS, where were they stored? How were they deployed? And what are they doing now? The swarm hypothesis suggests these fragments are not evaporating under solar heat. They are not ice. They might be rocky debris from the object's formation, or from some ancient collision. But they might also be probes, dormant machines waiting for proximity to an interesting target before activating. The dandelion seed concept that Loeb has discussed imagines tiny probes separating from a mothership and drifting toward planets for close observation. Such probes would be nearly undetectable, too small to reflect significant sunlight, too cold to produce thermal signatures. They could be passing through our solar system right now, and we would never know. I want to pause here and remind you that we are in theoretical territory. 3I-ATLAS is most likely a comet. The scientific consensus holds firm on this point. But the scientific method demands that we consider alternatives when anomalies accumulate, and the anomalies around 3I-ATLAS have accumulated to an extraordinary degree. 12 documented mysteries at last count, each one individually explicable through natural processes, but together they form a pattern that resists easy dismissal. The anatomy of a mothership is the anatomy of a question. What would it take to cross the void? What would it take to survive the journey? What would it take to arrive at a distant star and still function, still observe, still fulfill whatever purpose drove the construction of such an impossible vessel? We do not know the answers. We may never know. But asking the questions teaches us something about ourselves, about the limits of our engineering, about the scale of the universe, about the humility required when confronting something that exceeds our understanding. 3I-ATLAS will pass closest to Earth on December the 19th, 269 million kilometers, an enormous distance by human standards, but close enough for our best instruments to gather unprecedented data. In that window, we might learn something definitive. We might see the swarm resolve into a natural debris field, or dissolve into the optical artifacts of a mundane comet. Or we might see something else, something that forces us to expand our categories, something that transforms speculation into serious hypothesis. The anatomy of a mothership remains theoretical, but the object in our sky is real, and it is approaching. The engineering of interstellar arcs. We have talked about what a mothership might look like from the outside, the scale, the mass, the trajectory. But now we need to go deeper. We need to understand what it would actually take to engineer a vessel capable of functioning across interstellar distances and timescales. This is not idle speculation. Serious scientists have spent decades working on these problems. Project Daedalus, Project Icarus, Project Hyperion. Each of these initiatives has produced detailed technical analyses of interstellar travel requirements, and what they reveal is both humbling and illuminating. The challenges are immense, but they are not impossible, and understanding them helps us evaluate what 3I-ATLAS might actually be. The first and most fundamental challenge is propulsion. Getting a massive object up to interstellar velocities requires either enormous amounts of energy delivered quickly, or smaller amounts of energy delivered continuously over long periods. Chemical rockets, the kind we use today, are hopelessly inadequate. The rocket equation is merciless. To accelerate a payload to even a fraction of light speed using chemical propulsion would require fuel masses so enormous that the fuel itself becomes the primary payload. You end up needing fuel to carry the fuel to carry the fuel, an exponential spiral that makes the whole endeavour impossible. Nuclear propulsion offers better options. Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed using nuclear pulse propulsion. Small fusion bombs would be detonated behind the spacecraft, their expanding plasma caught by a magnetic pusher plate to provide thrust. The design called for 50,000 fusion pellets, each yielding about 1 gigajoule of energy. The total mission would accelerate a payload of several hundred tons to about 12% of light speed enough to reach Barnard's star in about 50 years. This is still slower than 3I-ATLAS would need for a reasonable journey time from most origin points, but it demonstrates that interstellar propulsion is within the realm of physics. It requires technology beyond our current capabilities, but not beyond physics itself. More advanced propulsion concepts include antimatter engines, where matter and antimatter annihilate to produce pure energy. The efficiency is theoretically perfect, converting 100% of fuel mass into thrust energy. The problem is producing and storing antimatter, which currently requires more energy than it releases and can only be created in microscopic quantities. A civilization with abundant energy and advanced manufacturing might solve this problem. They might have antimatter production facilities orbiting their home star, converting solar energy into fuel for interstellar voyages. There are also propulsion systems that do not require onboard fuel at all. Laser sails use powerful beams of light from the home system to push lightweight reflective sails to high velocities. The Breakthrough Starshot initiative proposes exactly this approach for sending tiny probes to Alpha Centauri. The advantage is that the heavy energy source stays home. The disadvantage is that you cannot decelerate at the destination without building another laser array there first. This makes laser sails excellent for one-way reconnaissance missions, but problematic for anything that needs to slow down and stay. 3I-ATLAS exhibits non-gravitational acceleration, a small but measurable push that modifies its trajectory beyond what gravity alone would predict. For a natural comet, this is explained by outgassing. As ices sublimate into vapor, the escaping gas provides a tiny thrust. But the observed acceleration of 3I-ATLAS requires an unusually large amount of mass loss. Calculations suggest that near perihelion, the object was losing around 4.4 million pounds per second. If this is natural sublimation, it implies either a very ice-rich composition or fragmentation that increased the total surface area available for sublimation. If it is not natural, it implies some other thrust mechanism. Perhaps residual propulsion from an ancient engine system. Perhaps thermal effects from internal heat sources. Perhaps something we cannot identify from our distant vantage point. The second major engineering challenge is structural integrity over long time scales. Human engineers design for decades. Bridges are meant to last a century. Nuclear waste storage facilities are designed for 10,000 years. But interstellar travel demands structures that function for millions of years. Nothing in human experience prepares us for this requirement. Even geological features change dramatically over such timescales. Mountains erode, continents drift. The very bedrock of Earth is impermanent over millions of years. Material science offers some hope. Certain crystalline structures are extremely stable. Diamond, for instance, is thermodynamically metastable, but kinetically stable, meaning it will not spontaneously convert to graphite under normal conditions for timescales far exceeding the age of the universe. Advanced ceramics, metallic glasses, and carbon nanotube composites all offer durability that exceeds conventional metals. A civilization with mature nanotechnology might build structures from the atomic level up, eliminating defects and grain boundaries that cause fatigue in bulk materials. Such structures could be self-healing, with embedded repair mechanisms that detect and fix damage automatically. The carbonaceous composition detected in 3I-ATLAS is interesting in this context. Carbonaceous materials include diamonds, graphite, carbon nanotubes, and fullerenes. Some of these are among the strongest and most durable materials known. A vessel built from advanced carbon composites would have excellent strength to weight ratios and good resistance to radiation damage. It would also be relatively stealthy, appearing dark against the blackness of space, absorbing rather than reflecting light. The third challenge is radiation shielding. Interstellar space is permeated by cosmic rays, high-energy particles that can damage electronics and cause cancer in biological organisms. Near stars, solar radiation adds additional hazards. Any vessel carrying sensitive cargo, whether living beings or delicate electronics, needs protection from this bombardment. On Earth, we are shielded by our atmosphere and magnetic field. In space, there is no such natural protection. Shielding can be passive or active. Passive shielding uses bulk material to absorb incoming radiation. Water is excellent for this purpose, providing good stopping power for most particle types while also being useful for other purposes. A thick layer of ice around a vessel's inner core would serve double duty as radiation shield and resource reserve. This is intriguing given that 3I-ATLAS appears to be shedding water ice from its surface. Is this a natural cometry process or the gradual ablation of a designed shield layer as the vessel approaches the Sun? Active shielding uses magnetic or electric fields to deflect charged particles. Earth's magnetosphere does this naturally. An artificial magnetosphere could protect a vessel without the mass penalty of bulk shielding. The technology required is substantial but not fantastical. Superconducting magnets could generate the necessary field strengths. A civilization with reliable high-temperature superconductors could make such systems lightweight and durable enough for interstellar service. The fourth challenge is energy. Everything we have discussed requires energy. Propulsion, structural maintenance, radiation shielding, life support if the vessel carries living beings, processing power if it carries artificial minds. Where does this energy come from during the long darkness between stars? Solar panels are useless far from any sun. Chemical batteries would be exhausted in years. Nuclear fission reactors have limited fuel supplies and generate problematic waste products. The most promising option is nuclear fusion. The same reaction that powers stars can be harnessed to power spacecraft. Fusion reactors using deuterium and helium-3 could potentially operate for centuries without refueling, and the fuel itself can be harvested from gas giant atmospheres or comet ices. A vessel approaching 3I-ATLAS's mass could carry enough fusion fuel to power itself for millions of years. The waste products are minimal and mostly non-radioactive. The energy density is enormous. An even more exotic option is antimatter catalyzed fusion, where tiny amounts of antimatter are used to trigger fusion reactions more efficiently than purely electromagnetic ignition. This reduces the amount of antimatter needed while still providing the performance benefits. A vessel designed around this technology could be remarkably compact for its capabilities, and there is one more possibility that pushes into truly speculative territory: vacuum energy extraction. Quantum field theory predicts that empty space contains enormous amounts of energy in its quantum fluctuations. This vacuum energy is real, demonstrated by the Casimir effect and other phenomena. But extracting useful work from it remains beyond our understanding. A sufficiently advanced civilization might have cracked this problem. They might draw power from the fabric of space-time itself, never needing fuel, never running down, operating indefinitely as long as space exists. The fifth and perhaps most difficult challenge is systems reliability. Any complex system will eventually fail. Components wear out. Software accumulates errors. Unexpected interactions between subsystems cause cascading malfunctions. Human spacecraft are designed for years or at most decades of operation, with the assumption that ground control can diagnose and sometimes fix problems remotely. An interstellar vessel has no such luxury. It must either be simple enough that nothing critical can fail, or sophisticated enough to diagnose and repair any conceivable failure autonomously. This drives design philosophy in interesting directions. Redundancy becomes paramount. Critical systems are duplicated, triplicated, or distributed across the entire structure so that no single point of failure can be catastrophic. Modularity allows damaged sections to be isolated and replaced without affecting the whole. Self-repair mechanisms, whether nanotechnological or simply clever mechanical design, handle routine maintenance without intervention. The swarm hypothesis takes on new meaning in this light. 1 trillion fragments distributed around a central body provides extreme redundancy. If some fragments are lost to micrometeorite impacts or radiation damage or simple system failure, the swarm continues. The distributed nature of the system protects against catastrophic single-point failures. It also allows specialization. Different fragments could serve different functions: communication, sensing, computation, storage, with the central body coordinating their activities. Project Hyperion, a recent initiative to design a crewed interstellar vessel for a 250-year journey, grappled with exactly these issues. Their conclusions were sobering. A minimum population of several hundred people would be needed for genetic viability. Multiple redundant closed ecosystem loops would be required for life support. The vessel would need to be essentially self-sufficient, capable of manufacturing replacement parts, growing food, recycling every molecule of waste. The design that emerged resembled less a spacecraft than a small mobile city, complete with agriculture, industry, medical facilities, and all the infrastructure of a functioning society. 3I-ATLAS is large enough to contain such a city. Its mass exceeds anything Project Hyperion imagined. If it is artificial, it was built by a civilization that solved all these engineering challenges and more. A civilization that looked at the void between stars and saw not an impassable barrier, but a highway waiting to be travelled. But here is the deepest question of all. Even if you solve the engineering, even if you build a vessel that can survive the journey, what do you put inside it? What kind of life can endure timescales measured in geological epochs? What kind of mind stays sane across millennia of darkness? What kind of being emerges at the destination, still recognizable as whatever began the journey? These questions lead us into territory that is less engineering and more philosophy, less physics and more biology, less science and more speculation. But they are questions we must ask if we want to truly understand what 3I-ATLAS might be, and what it might contain. Life that survives the void. Let us pause and consider something remarkable. Life on Earth has proven far more resilient than anyone imagined possible. In the harshest environments our planet offers, places we once assumed were sterile wastelands, we find organisms thriving. Boiling hydrothermal vents at the bottom of the ocean, frozen Antarctic ice sheets, acidic volcanic pools, the crushing depths beneath miles of rock. Everywhere we look, life finds a way. These extremophils, as we call them, have rewritten our understanding of biological limits, and they have profound implications for what might survive an interstellar journey. Consider the tardigrade. This microscopic animal, sometimes called a water bear, can survive conditions that would instantly kill any other known organism. Temperatures near absolute zero, temperatures above the boiling point of water, radiation doses 1,000 times what would be lethal to humans, the vacuum of space, complete desiccation for decades. Tardigrades achieve this through a process called cryptobiosis, essentially shutting down all metabolic activity and entering a state of suspended animation. In this state, they are not truly alive in any conventional sense, but they are not dead either. They persist, they endure, and when conditions improve, they wake up and continue as if nothing happened. If Earth can produce tardigrades through random evolution, what might billions of years of directed evolution produce elsewhere? What extremophils might exist on worlds we have never seen, adapted to conditions we have never imagined? The possibilities are both wondrous and unsettling. Life could exist in forms so alien to our experience that we might not recognize it as life at all. This matters for 3I-ATLAS, because any biological travelers inside an interstellar vessel would need to survive conditions that make Antarctica look tropical. The space between stars is cold. Not just cold, but profoundly existentially cold. Background temperature in interstellar space is about 2.7 Kelvin, less than 3 degrees above absolute zero. At these temperatures, most chemical reactions effectively stop. Molecular motion slows to a crawl. Biological processes, as we understand them, become impossible. Yet life on Earth has demonstrated remarkable cold tolerance. Bacteria have been revived after spending millions of years frozen in Antarctic ice. The bacterium Carnobacterium pleistocenium was recovered from Alaskan permafrost dating back 32,000 years to the Pleistocene era. It was not merely preserved, but still viable, able to grow and reproduce when thawed and provided with nutrients. This survival across geological time suggests that the mechanisms of cold tolerance are more robust than we assumed. The key is not avoiding freezing, but surviving it. When cells freeze, ice crystals form that can puncture cell membranes and destroy internal structures. Some organisms produce antifreeze proteins that lower the freezing point of their body fluids. Others produce compounds that control where ice crystals form, keeping them outside the cells where they cause less damage. Still others replace water in their cells with trehalose, a sugar that forms a glass-like solid when dried, protecting proteins and membranes during desiccation. And advanced civilization engineering organisms for interstellar travel could enhance these natural mechanisms far beyond what evolution achieved randomly. Gene therapy could insert antifreeze proteins into every cell type. Nanotechnology could provide scaffolding that prevents ice crystal growth. Controlled slow freezing could allow water to be removed gradually, preventing thermal shock. The result might be organisms that could be frozen solid for millions of years and then revived with minimal damage. But freezing is only one challenge. Radiation is another. Cosmic rays bombard any object in interstellar space. delivering doses that would be lethal to unprotected humans within months. The longer the journey, the more radiation damage accumulates. DNA is particularly vulnerable. Radiation causes breaks in the DNA strand, mutations in the genetic code, and damage to the cellular repair machinery that normally fixes such problems. Yet here too, life has found solutions. The bacterium Deinococcus radiodurans can survive radiation doses over 1,000 times what would kill a human. It achieves this not by preventing DNA damage but by repairing it with extraordinary efficiency. Its genome exists in multiple copies, providing templates for reconstruction. Its repair enzymes work with remarkable speed and accuracy. Even when its DNA is shattered into hundreds of fragments, it can reassemble the pieces correctly within hours. Imagine engineering this capability into the cells of an interstellar traveler. Multiple redundant copies of every gene. Enhanced repair mechanisms working continuously to undo radiation damage. Perhaps artificial chromosomes that store backup copies of critical genetic information. Perhaps nanoscale repair machines that patrol the body, detecting and fixing damage before it causes problems. The result might be an organism that could survive indefinite radiation exposure, living forever in the radioactive environment of deep space. The combination of cold tolerance and radiation resistance suggests something profound. The interstellar void, which seems utterly hostile to life, might actually be survivable for properly adapted organisms. The cold that stops biological processes could also stop aging, preserving tissues in a state of suspended animation, while radiation damage is slowly repaired by the minimum biological activity needed to maintain cellular integrity. An organism in this state would not be living in any active sense. It would be waiting, persisting, enduring across timescales that dwarf anything we consider possible for life. Now consider what we know about 3I-ATLAS. It has been travelling through interstellar space for billions of years according to some trajectory analyses. 10 billion years, as old as the galaxy itself. If it carries life, that life has been in transit for longer than the Earth has existed. Longer than our solar system has existed. For this to be possible, the organisms involved would need to survive not millennia but eons. Every adaptation we discussed would need to function flawlessly across timescales that strain comprehension. This seems impossible, and perhaps it is for biological life as we understand it. But there are other possibilities. What if the travellers are not biological at all? What if they began as biological organisms but transcended those limitations long before their journey began? Mind uploading is a concept that appears frequently in discussions of advanced civilizations. The idea is that consciousness, being ultimately a pattern of information processing, could theoretically be transferred from a biological brain to an artificial substrate, a silicon-based computer, a quantum processor, a network of molecular machines. The resulting entity would still be a mind, still be a person, in some meaningful sense, but it would no longer depend on fragile biological machinery for its existence. Such a digital consciousness would face none of the challenges that plague biological interstellar travellers. It would not need food, water, or atmosphere. It would not age in any biological sense. It could be stored in multiple redundant copies, surviving hardware failures that would kill any single instantiation. It could slow its processing down to minimal levels during transit, experiencing the journey as a brief pause rather than an endless wait. It could even stop entirely, stored as inert data, and be restarted at the destination with no subjective awareness of the time past. The swarm hypothesis takes on new meaning in this context. 1 trillion fragments could each contain processing hardware. Each could instantiate separate minds or portions of a distributed consciousness. The swarm itself could be a civilization, a population of digital beings travelling together through the void. They would communicate via signals between fragments, forming a network stretched across thousands of kilometers of space. They would think and decide and experience just not in any way our brains could comprehend. This possibility is unsettling precisely because it is plausible. We are already taking the first steps toward brain-computer interfaces, toward understanding consciousness as information, toward the technologies that might eventually allow such transcendence. If we could conceive of it with our mere century of technological development, a civilization millions or billions of years older than ours could certainly achieve it. They might look back at biological existence the way we look back at single-celled life, as a primitive stage long since surpassed. But there is another possibility, perhaps even stranger. What if the travelers are neither biological nor digital, but something in between? Hybrid organisms that combine organic and synthetic components. Cyborgs in the truest sense, blending the adaptability of biology with the durability of technology. Such beings might have biological cores that provide consciousness and creativity, surrounded by technological enhancements that provide protection and capability. Nanoscale machines in their bloodstreams could repair radiation damage in real time. Artificial organs could provide nutrition from raw materials without need for food. Synthetic nervous systems could interface with external devices, allowing direct control of spacecraft systems or distributed components. During transit, the biological core could be placed in suspended animation, frozen solid while the technological components maintained minimal operations. Slow repair processes could fix accumulated damage. Monitoring systems could watch for problems and intervene if needed. Upon arrival, the biological component could be revived, the person awakening to find themselves orbiting a new star, their technological extensions already gathering data about this unknown system. This is speculative, deeply speculative. We have no evidence that 3I-ATLAS contains anything like what I am describing. The most likely explanation remains that it is a natural comet, strange and unprecedented, but natural nonetheless. But if we are to seriously consider the alternative, we must think through what that alternative implies. And what it implies is that life capable of interstellar travel would be almost unrecognizable to us. It would have transcended limitations we consider fundamental. It would exist on timescales we can barely imagine. It would be as far beyond us as we are beyond bacteria. That thought should inspire humility. We are young. Our civilization is young. Our technology is young. We look at 3I-ATLAS and try to understand it with tools and concepts developed over mere centuries of scientific inquiry. If it is artificial, it was built by beings who have been doing science for millions of times longer than us. Our confusion, our uncertainty, our inability to determine its true nature might simply reflect the vast gulf between our understanding and theirs. December the 19th approaches. The object draws closer, and somewhere inside it, or around it, or distributed through the swarm that may accompany it, there might be something waiting, watching, making decisions about what to do with the curious young civilization that noticed its passage. What would such beings think of us? What would they want from us? What would they fear from us? These questions have no answers yet, but they are questions we must ask as we explore what kinds of life could possibly survive the journey 3I-ATLAS has made. The frozen passengers. Suspended animation has haunted human imagination for as long as we have dreamed of the stars. The idea is seductive in its simplicity. You cannot survive a journey of centuries or millennia while awake, experiencing every endless moment. So you sleep through it. You freeze yourself solid, stop all biological processes, and let time pass unnoticed until you arrive at your destination. In fiction, this is almost trivial. The hero enters a pod, the lights dim, and the next scene shows them waking up at a new world. In reality, the challenges are immense, but they may not be insurmountable, and understanding them helps us imagine what might be frozen inside 3I-ATLAS, waiting to thaw in the light of an alien sun. Cryopreservation, the science of preserving biological materials at extremely low temperatures, has made remarkable advances in recent decades. We can successfully freeze and thaw human eggs, sperm, and embryos. We can cryopreserve blood, bone marrow, and certain tissues. Entire organs remain challenging, but progress is being made. The fundamental problem is ice. When water freezes, it forms crystals. These crystals expand, rupturing cell membranes and destroying the delicate internal structures that make cells function. Freeze a complex organ carelessly, and you produce biological mush, not a viable transplant. The solution lies in vitrification rather than freezing. Vitrification means cooling something so quickly that water molecules do not have time to organize into crystals. Instead, they form an amorphous glass, solid but structureless, preserving the spatial relationships between molecules without the damaging expansion of ice. Achieving vitrification requires extremely rapid cooling rates and often the use of cryoprotectants, chemicals that further inhibit ice crystal formation. This is where the technology becomes speculative for interstellar applications. Vitrifying an entire human body is beyond current capabilities. The cooling must be rapid throughout the entire volume, which is difficult for anything larger than small tissue samples. The concentrations of cryoprotectants needed can themselves be toxic. And most importantly, we have never successfully revived a vitrified mammal. We do not know if the brain, with its extraordinarily complex neural connections, can survive the process intact. But consider what an advanced civilization might achieve. Nanotechnology could provide cryoprotection at the cellular level, with tiny machines delivering protective compounds directly to where they are needed. Genetically engineered cells could be more resilient, with enhanced membrane structures and proteins that facilitate safe vitrification. Controlled cooling using precisely modulated magnetic fields could achieve uniform temperature reduction throughout even large bodies. And most importantly, if a civilization had millions of years to perfect the technique, they could solve problems through trial and error that we can barely formulate. The passengers of an interstellar ark could enter suspended animation before departure, their bodies vitrified and stored in carefully maintained conditions for the duration of the voyage. They would not age, they would not experience time passing, they would not suffer the psychological torment of eternal confinement. From their perspective, the journey would be instantaneous. They would close their eyes in orbit around their home star and open them in orbit around a new one, the billions of kilometers between traversed in what felt like a single night's sleep. But this raises profound questions. Who decides who gets frozen? On a generation ship with a living population, society continues during the voyage. Children are born, leaders rise and fall, cultures evolve. The people who arrive might be very different from those who departed, shaped by centuries of unique experience in their enclosed world. With suspended animation, the original passengers arrive unchanged. The society that built the ship, with all its values and conflicts and cultural assumptions, is preserved whole. This is both advantageous and troubling. Advantageous because it maintains continuity. The original mission objectives, whatever they were, remain fresh in minds that have not had millennia to reinterpret them. Troubling because it freezes not just bodies, but ideas. Whatever problems or limitations existed in the launching civilization travel with them unchanged. There is no opportunity for growth, reflection, or the wisdom that comes from long experience. Some theoretical models propose a hybrid approach. Most passengers remain frozen for the bulk of the journey. A small crew operates in shifts, each group awakened for a period of decades or centuries before being refrozen, while another group takes over. This allows the ship to respond to unexpected situations while minimizing the social and psychological challenges of multi-generational travel. The crew develops institutional knowledge that is passed down through overlapping watch periods, maintaining continuity of purpose across timescales that would otherwise be incomprehensible. 3I-ATLAS has been traveling for a very long time, 10 billion years by some estimates. Even with perfect suspended animation technology, there are limits to how long biological materials can remain viable. Cosmic radiation continuously damages DNA and other molecules. Low-level, quantum effects cause gradual degradation even at temperatures near absolute zero. Over millions of years, these effects accumulate. After billions of years, it seems unlikely that any biological passengers would remain viable for revival, unless the ship includes active maintenance systems. Nanoscale machines patrolling through frozen tissue, repairing damage as it occurs, replacing degraded molecules with fresh copies assembled from stored materials. This is speculative technology, but not fundamentally impossible. We already use nanotechnology for drug delivery and imaging. The step from there to cellular repair is large but not magical. A civilization advanced enough to build an interstellar ark would likely have such capabilities. The swarm hypothesis suggests another possibility. Perhaps the passengers are not inside the central body at all. Perhaps they are the swarm itself. Each of the trillion fragments could be a cryopod, a small vessel containing one or more suspended individuals. The distributed architecture would provide redundancy against damage. If some pods are lost to impacts or radiation or system failures, others survive. The population as a whole persists even if individual members do not. This would explain the unusual stability of the swarm structure. Active station keeping, powered by minimal energy sources, could maintain the formation across interstellar distances. Communication between pods could allow coordination. A central control system, perhaps housed in the main body of 3I-ATLAS, could manage the swarm as a whole, making decisions about trajectory corrections, damage response, and eventually revival and deployment at the destination. When I think about frozen passengers, I also think about what they might be fleeing or seeking. Interstellar travel is not undertaken lightly. Even for a civilization with the technology to make it possible, the investment of resources and time is staggering. You do not build an ark carrying billions of tons across light years for casual exploration. You do it because you must, because something at home has become untenable, because you have found something at your destination worth any cost to reach. The history of life on Earth is punctuated by catastrophes, mass extinctions, asteroid impacts, volcanic super-eruptions, climate collapses. Each time, most species perished and a few survivors rebuilt. A technological civilization facing such a catastrophe might choose to ensure survival by sending some portion of themselves to the stars. Not to colonize, but to preserve. Not to conquer, but to endure. If 3I-ATLAS carries frozen refugees from such a catastrophe, they have been travelling since before our solar system existed. Their homeworld, wherever it was, is certainly gone now. The star it orbited has likely gone through its entire life cycle, swelling into a red giant or detonating as a supernova, destroying everything that once existed there. The passengers would be the last survivors of a civilization that vanished billions of years ago. Relics of a past so ancient that even the geography of the galaxy has shifted since they departed. What would such beings want if they were revived today? Their home is gone. Their species is almost certainly extinct except for whoever remains frozen in this vessel. They would be orphans in a universe that has moved on without them. Would they seek to rebuild? Would they try to find others like themselves, following old signals to rendezvous points that no one has visited for eons? Would they look at Earth and see a new home, a place where their civilization could begin again? These questions venture into psychology and philosophy more than science. We cannot know what alien minds would want or fear or hope, but we can recognize that the passengers of an interstellar ark, if they exist, would face existential challenges beyond anything human experience prepares us to imagine. The loneliness of being the last of your kind, the disorientation of waking in a universe utterly different from the one you left, the burden of carrying an entire civilization's legacy in your memories and your DNA. The cryovolcanoes recently observed on 3I-ATLAS add an intriguing detail to this picture: ice volcanoes erupting as the comet approaches the sun. If the object is natural, these are simply pockets of volatile ices vaporizing under solar heating. But if the object is artificial, they could be something else: coolant systems venting excess heat, damaged cryo chambers breaching their containment, or deliberate thawing, the beginning of a revival process triggered by proximity to a star. This last possibility is haunting. 3I-ATLAS passed closest to the Sun on October the 29th. It is now receding, heading toward its December 19th close approach with Earth. If revival systems activated at perihelion, when solar energy was most abundant, any passengers could be thawing right now. Coming back to awareness after billions of years, looking out at the unfamiliar stars, trying to understand where they are and what has happened while they slept. What would they see when they looked at Earth? A water world teeming with life, electromagnetic emissions suggesting a technological civilization, one that has noticed them, tracked them, analyzed them, speculated about them. Would they be curious? Would they be cautious? Would they see us as potential allies or potential threats? The next chapter explores not frozen passengers but frozen alternatives. Forms of life that do not need to sleep through the journey because they are built for the cold. Alternative biochemistries that thrive where water and carbon-based life would perish. The strange possibilities that emerge when we stop assuming alien life must resemble life on Earth. Alternative biochemistries. Everything we have discussed so far assumes life similar to our own, carbon-based, water-dependent, operating, within temperature ranges that allow liquid water to exist. But there is no law of physics that requires life to work this way. Carbon and water happen to be abundant and versatile on Earth, so evolution exploited them. On other worlds, with different conditions and different resources, life might have found entirely different solutions, and some of those solutions might be far better suited to interstellar travel than anything Earth biology could achieve. Let us start with the element that most often appears in discussions of alternative biochemistry: silicon. On the periodic table, silicon sits directly below carbon. Both elements have 4 valence electrons, meaning they can form 4 chemical bonds with other atoms. This gives them similar potential for building complex molecular structures. Carbon forms the backbone of proteins, DNA, sugars, and fats. Could silicon do the same? The short answer is complicated. Silicon can form chains with itself, just as carbon does in organic molecules. But silicon-silicon bonds are weaker than carbon-carbon bonds and more reactive. In the presence of water and oxygen, silicon tends to form silicon dioxide, the primary component of sand and glass. This is far more stable than the complex chains life requires. On Earth, silicon chemistry tends toward rocks rather than biology. But consider a world very different from Earth. A world without liquid water or free oxygen. A world cold enough that chemical reactions proceed slowly, allowing fragile silicon structures to persist longer before breaking down. On such a world, silicon-based life might be possible. The slow reaction rates would mean slow metabolism, perhaps minds that think on timescales of centuries rather than seconds. But slow is not the same as impossible. Saturn's moon Titan offers a tantalizing glimpse of such conditions. Titan has lakes and seas of liquid methane and ethane rather than water. Its surface temperature hovers around -180 degrees Celsius. At these temperatures, carbon-based chemistry largely stops. But silicon chemistry might actually work better. The extreme cold would stabilize otherwise reactive silicon compounds. Liquid methane, unlike water, does not aggressively attack silicon structures. If life could arise under such conditions, it would be fundamentally alien to us. It would metabolize differently, obtaining energy through chemical reactions we would barely recognize as biological. It would think differently, if it thought at all, with neural processes operating on timescales that make our cognition seem like lightning. It would experience time differently, perhaps not distinguishing between years and decades in any meaningful way. Now consider how such life would experience interstellar travel. For a silicon-based organism evolved in cryogenic conditions, the cold of interstellar space would not be hostile. It would be comfortable, perhaps even warm compared to home, the journey that would kill. A human in seconds might be pleasant for such a being. The billions of years of transit that seem impossible for carbon life might pass like a long but tolerable voyage. 3I-ATLAS shows chemical signatures that mainstream scientists attribute to its unusual composition. Metal-rich, but with strange ratios. Nickel abundant, but iron scarce. Carbon compounds venting from its surface. None of this proves silicon-based life. All of it can be explained by natural processes. But it is worth noting that if silicon life existed, we would not necessarily recognize it. Our instruments are calibrated for carbon chemistry. Our biological models assume water and oxygen. Something genuinely alien might look like nothing more than interesting geology. Silicon is not the only alternative to carbon. Theoretical biologists have proposed numerous other possibilities. Sulfur-based life might exist in volcanic environments, metabolizing sulfur compounds the way we metabolize carbon. Such organisms might thrive near hydrothermal vents on ocean moons or in the atmosphere of Venus, where sulfuric acid clouds create conditions toxic to carbon life, but potentially habitable for sulfur metabolizers. Ammonia could substitute for water as a biological solvent. Ammonia remains liquid at much lower temperatures than water, from -78 to -33 degrees Celsius at standard pressure. Organisms using ammonia as their internal medium could remain active in cold environments, where water-based life would freeze solid. Their proteins and other biological molecules would be structured differently, optimized for ammonia chemistry rather than water chemistry. But the basic principles of complex molecular organization could still apply. Hydrogen fluoride is another candidate solvent, remaining liquid across a wide temperature range and capable of forming hydrogen bonds similar to water. Liquid hydrocarbons like methane could serve the same function at even lower temperatures. Each alternative solvent enables different chemistry, different molecular structures, different metabolic pathways. Each produces organisms that would be unrecognizable by Earth standards, yet still qualify as life by any reasonable definition. The implications for 3I-ATLAS are speculative but worth considering. We do not know where this object originated. We do not know what conditions existed on its homeworld or in the stellar system it came from. If it is artificial, if it was built by an intelligent species, that species might have biochemistry utterly unlike our own. Their construction materials might be chosen for properties we do not understand because our science never evolved to consider them. The carbon dioxide-rich emissions from 3I-ATLAS are interesting in this context. Carbon dioxide is waste product for Earth life. It could be a resource for organisms with different metabolisms. Some bacteria on Earth already fix carbon dioxide into organic compounds through chemosynthesis rather than photosynthesis. An alien metabolism might go further, using carbon dioxide as a primary building block or energy source. The nickel-rich but iron-poor composition is even more intriguing. Iron is essential for Earth life, central to hemoglobin and numerous enzymes. Nickel plays a smaller but still important role. An organism that used nickel where we use iron would have fundamentally different biochemistry. Its blood, if it had blood, would not be red. Its enzymes would catalyze different reactions at different rates. Its entire metabolism would operate according to rules we would need to discover from scratch. I want to be careful here. Nothing we have observed proves that 3I-ATLAS contains or was built by alternative life forms. The chemical signatures have natural explanations. Unusual cometary composition does not require biological origins. But when we speculate about what might be inside an interstellar visitor, we should not limit ourselves to carbon copies of Earth life. The universe is vast and old and weird. Whatever exists out there has had billions of years to evolve solutions we have not imagined. There is another possibility that blurs the line between life and non-life entirely. What if the travellers are not biological in any sense we would recognise? What if they are complex chemical systems that exhibit lifelike properties without being alive by Earth definitions? Self-organising, self-replicating, adaptive, intelligent even, but built from materials and processes that do not fit any biology textbook. Autocatalytic chemical networks can exhibit surprisingly lifelike behaviours, a set of reactions where the products catalyse their own production, leading to exponential growth. Coupled reaction systems that maintain stable states far from equilibrium mimicking homeostasis. Chemical oscillators that produce rhythmic patterns, analogous to heartbeats or neural oscillations. None of these are alive in the traditional sense, but they share properties with life that suggest a continuum rather than a sharp boundary. A sufficiently complex autocatalytic network might achieve something like cognition, patterns of chemical concentration that represent information, reaction pathways that compute optimal responses to environmental stimuli, memory encoded in molecular concentrations, learning through modification of catalytic efficiencies. This is speculative to the point of science fiction, but it is not impossible, and an interstellar vessel might contain something like this. A chemical intelligence utterly alien to our carbon-centric assumptions. The vacuum of space presents special challenges, but also special opportunities for alternative life. Without atmospheric interference, exotic chemical systems could persist that would be unstable on any planetary surface. Plasma-based life is theoretically possible, with charged particles in stellar atmospheres forming organized structures that metabolize, replicate, and evolve. Magnetic field life might exist near pulsars or magnetars, with organized field configurations storing and processing information. These ideas push the boundaries of what we consider possible, but boundaries exist to be pushed. When I think about 3I-ATLAS, I try to keep my mind open to all these possibilities. The object might be a natural comet, strange but explicable through known physics. It might be an artificial vessel carrying carbon-based passengers in suspended animation. It might contain silicon beings comfortable in the interstellar cold. It might host chemical intelligences we would not recognize as alive. It might be something else entirely, something our science has not yet learned to conceptualize. The swarm hypothesis accommodates all these possibilities. 1 trillion fragments could be natural debris from a cometary nucleus. They could be escape pods containing carbon organisms. They could be autonomous probes built by silicon engineers. They could be distributed components of a chemical intelligence spread across thousands of kilometers of space. The data we have does not distinguish between these scenarios. Only more observation, more analysis, more creative interpretation might eventually reveal the truth. December 19th will not answer all our questions. The close approach will provide better images, better spectra, better constraints on what 3I-ATLAS might be. But it will not tell us definitively whether life is present or what form that life might take. Some mysteries take centuries to solve. Some take millennia. Some may never be fully resolved. leaving humanity forever wondering about the strange visitor that passed through our solar system in the year 2025. But wondering is not nothing. Asking questions is not nothing. The mere fact that we are considering these possibilities, stretching our minds to imagine life forms utterly unlike ourselves, represents a kind of growth. We are preparing ourselves for a universe that might be far stranger and more wonderful than we ever assumed, and that preparation, whatever 3I-ATLAS turns out to be, has value in itself. The trillion fragment problem. We return now to the numbers. A trillion fragments. That is what Avi Loeb's calculations suggest might surround 3I-ATLAS, producing the anomalous sunward anti-tail that has puzzled observers since July. A trillion is a difficult number to comprehend. It is a million, 1,000 billion. If you counted one number per second, it would take you over 31,000 years to reach a trillion. The fragments could not be counted by any human process. They exceed human comprehension. And yet physics demands we take them seriously. Loeb's math is straightforward. The non-gravitational acceleration of 3I-ATLAS is measured and documented in JPL Horizon's data. This acceleration creates a differential between the primary body and any accompanying fragments that do not share the same response to solar radiation pressure. Over the vast distances involved, this differential produces a predictable offset. The offset matches the observed angular separation of the sunward anti-tail from the main nucleus. One explanation for this match is coincidence. Another is that the anti-tail really is a swarm of solid objects drifting in the wake of 3I-ATLAS. The trillion figure comes from calculating what such a swarm would look like. If the fragments together weigh just 1,000th of the primary body's mass, and if they are distributed across the observed volume of the anti-tail, you need roughly 1 trillion pieces to match the observed brightness. This is because small fragments have much higher surface area to mass ratios than large objects. A single boulder reflects a certain amount of light. Crush that boulder into dust and the total reflective surface area increases enormously. 1 trillion tiny fragments could produce 100 times more reflected light than the main body of 3I-ATLAS itself. This has staggering implications. If the swarm hypothesis is correct, most of what we have been photographing is not 3I-ATLAS at all. It is the clouds surrounding it. The teardrop-shaped coma, the streaming anti-tail, the luminous glow that makes this interstellar visitor visible across hundreds of millions of kilometers. All of it could be the swarm rather than the nucleus. But this raises questions that do not have easy answers. Where did 1 trillion fragments come from? How have they maintained formation across billions of years of interstellar travel? Why do they not disperse into the void, scattering beyond any hope of observation? The physics that creates the swarm also tends to destroy it. Solar radiation pressure should push on the fragments. Gravitational interactions should perturb their orbits. Random collisions should change velocities and directions. Over millions of years, let alone billions, any cloud of debris should dissipate into nothing, unless something holds it together. This is where speculation becomes necessary. One possibility is gravitational binding. If the fragments orbit the central body of 3I-ATLAS in a stable configuration, they could remain associated indefinitely. But the observed distribution of the anti-tail extends far beyond any plausible gravitational sphere of influence. At distances of hundreds of thousands of kilometers, the gravity of 3I-ATLAS is negligible compared to solar gravity. The fragments are not gravitationally bound. They are something else. Another possibility is electromagnetic binding. Charged particles in plasma can form coherent structures across vast distances, maintained by magnetic field interactions. Some comets exhibit magnetic effects in their ion tails. If 3I-ATLAS generates or carries a significant magnetic field, it might influence the motion of charged fragments in ways that maintain coherence. This would require the fragments themselves to be conductive or to carry electric charge, which is not typical of cometary debris, but not impossible either. A third possibility is active station keeping. The fragments might not be passive debris, but active devices, each equipped with minimal propulsion capabilities that allow them to maintain formation. This sounds like science fiction, and it probably is. But if 3I-ATLAS is artificial, if it was designed and built by an intelligence rather than formed through natural processes, then active station keeping becomes not just possible but expected. You would not release 1 trillion autonomous devices without some mechanism for coordination. The alternative is that the swarm is a recent phenomenon. Perhaps 3I-ATLAS was a single coherent body until something happened near perihelion. The intense solar heating, 770 watts per square meter at closest approach, could have triggered fragmentation. Ice pockets beneath the surface could have explosively vaporized, shattering portions of the nucleus. A weakly bound rubble pile could have disaggregated under thermal stress. The swarm we observe now might have formed only weeks ago, during the period when the object was hidden behind the Sun from Earth-based observation. This scenario aligns with observations of increased mass loss near perihelion. The rate jumped from about 330 pounds per second in early August to 4.4 million pounds per second near closest solar approach. That is an increase of over 13,000 times. Such dramatic escalation suggests something violent happened, not the gradual sublimation of surface ices, but a catastrophic event that exposed new material and vastly increased the available surface area. Loeb has proposed that this mass loss implies fragmentation into at least 16 major pieces, each contributing its own sublimation output. The trillion small fragments would be in addition to these larger chunks, a hierarchy of debris ranging from kilometre-scale boulders down to microscopic dust. The whole assemblage would be expanding, each component on a slightly different trajectory, the swarm slowly dispersing as it recedes from the Sun. If this interpretation is correct, we are witnessing the death of 3I-ATLAS. Not a sudden explosive end, but a gradual dissolution, the ancient interstellar visitor coming apart under forces it was never designed to withstand. A natural comet breaking up is interesting, but not unprecedented. Comet Shoemaker-Levy 9 famously disintegrated and slammed into Jupiter as a string of fragments in 1994. Comet Atlas from 2020 disintegrated as it approached the Sun, disappointing skywatchers who had hoped for a spectacular naked-eye display. But if 3I-ATLAS is artificial, its fragmentation takes on different meaning. Designed structures fail for different reasons than natural objects. Mechanical systems have operating limits. Thermal management systems can be overwhelmed. Damage accumulated over billions of years might finally exceed repair capabilities. An artificial vessel breaking apart near our Sun would be a tragedy of cosmic proportions, a technological marvel succumbing to forces it had survived for eons, failing at last in full view of the first technological species it had ever encountered. The trillion fragment problem also connects to the question of what the fragments are made of. Natural cometary debris consists of ice and rock, mixed in varying proportions. The ice sublimates when heated, producing the characteristic glow of a comet's coma. Rock particles persist longer, but eventually spread out under solar radiation pressure. Neither material would maintain coherent structure for billions of years of interstellar travel. Neither explains why the anti-tail points toward the Sun rather than away from it. Loeb notes that the fragments appear not to sublimate under solar heating. Whatever they are made of, they do not behave like ice. This places them outside the category of typical cometary particles. They could be rocky debris, weathered by cosmic radiation into stable forms that resist further change. They could be metallic, shards of processed material from whatever created 3I-ATLAS. They could be synthetic, manufactured substances with properties optimized for durability and reflectivity. The nickel-rich composition of 3I-ATLAS emissions suggests industrial processing. Nickel alloys are common in human manufacturing, valued for their strength, corrosion resistance, and high temperature stability. An artificial structure would likely incorporate nickel alloys in critical components. If such a structure were fragmenting, the debris would contain elevated nickel levels. This is not proof of artificial origin, but it is consistent with that hypothesis. Each observation adds a piece to the puzzle without completing the picture. The trillion fragments explain the brightness and distribution of the anti-tail. The non-sublimating composition explains why the anti-tail persists. The recent fragmentation explains why the swarm exists at all. But none of this tells us definitively whether we're looking at a natural comet coming apart or an artificial vessel failing after billions of years of service. December the 19th offers one more opportunity to gather data. As 3I-ATLAS reaches its closest approach to Earth, telescopes around the world will image it with the best resolution the geometry allows. They will look for structure within the swarm, evidence of organized distribution rather than random dispersal, signs that some fragments are behaving differently from others, perhaps maintaining specific positions or following coordinated trajectories. What they find could transform our understanding of this object, or it could leave us with more questions than answers. The trillion fragment problem might be solved, at least in part, by better observation. Or it might deepen into mystery, each new detail adding complexity without resolution. Either way, we are learning something important. The universe sends us objects we do not understand, objects that challenge our categories and exceed our expectations, objects that force us to think harder, observe more carefully, and question assumptions we did not know we held. 3I-ATLAS is such an object. The trillion fragments that may surround it are part of its enigma, and our struggle to understand them is part of what it means to be a young species taking its first steps into the cosmic unknown. December 19th. 16 days from now, the geometry of our solar system will align in a way that does not happen often. 3I-ATLAS will reach its closest distance to Earth, 269 million kilometers, 1.8 astronomical units, nearly twice the distance from here to the Sun. It sounds far, and it is far by any human standard. A journey at highway speeds would take over 300,000 years. Even light takes almost 15 minutes to cross that distance. And yet, by the standards of interstellar observation, this is intimate. This is close. This is our best chance to see what we are dealing with. Every major observatory on Earth is preparing. The Hubble Space Telescope will dedicate observation time. The James Webb Space Telescope will turn its infrared eyes toward the visitor. Ground-based instruments from Hawaii to Chile to the Canary Islands will coordinate their efforts, building up exposure time through careful tracking of the fast-moving object. Amateur astronomers with large backyard telescopes are calibrating their equipment, planning multi-hour imaging sessions, hoping to capture something the professionals might miss. NASA has been notably active in coordinating these observations. Their statement emphasizes that 3I-ATLAS poses no threat to Earth and will remain far away. This is reassuring language meant for public consumption. Behind the scenes, the level of attention being paid to this object suggests something more than routine cometary monitoring. Every available asset is being deployed. Mars orbiters captured images during the October close approach to the red planet. The Punch satellites observed it during perihelion. SOHO and Stereo watched it transit near the Sun. Now Earth-based instruments take the lead as the object enters the optimal observation window. What are they looking for? At the most basic level, they want better images, higher resolution pictures of the nucleus and coma, more detailed spectra showing exactly what chemicals are present and in what proportions, better tracking data to refine our understanding of the trajectory and any non-gravitational accelerations. These are standard scientific objectives for any unusual comet. But there are also specific questions that December 19th might answer. The swarm hypothesis predicts a particular distribution of material around the primary body. If the anti-tail really consists of solid fragments rather than gas and dust, high-resolution imaging should reveal structure, clumps and filaments and gaps where natural debris would show smooth gradients, evidence that the distribution is organized rather than random. The jets observed streaming from 3I-ATLAS after perihelion have puzzled scientists. They are straight and rigid, maintaining their orientation across distances of over 1 million kilometers, despite the object's measured rotation period of about 16 hours. Natural cometary jets should twist and curl as the nucleus rotates, producing spiral patterns in the surrounding gas. The jets from 3I-ATLAS do not do this. They point in fixed directions relative to the Sun regardless of how the nucleus is oriented. This is one of the 12 anomalies Loeb has catalogued, and it remains unexplained by conventional cometary science. December 19th, observations might reveal whether this persistence continues as the object recedes from the Sun. As solar heating decreases, natural jets should weaken and perhaps change character. If the straight jets persist, it would suggest something other than simple volatile sublimation is producing them. The chemical composition will be scrutinized with unprecedented detail. Early observations showed that 3I-ATLAS is rich in carbon dioxide and carbon monoxide, but relatively poor in water compared to solar system comets. The ratio of carbon dioxide to water ice is 8:1, among the highest ever recorded for any comet. This suggests an origin in a stellar system very different from our own, perhaps around a star cooler than the Sun, or in a disk with different chemical abundances. But composition alone does not distinguish natural from artificial. A comet could have unusual chemistry simply because it formed in unusual conditions. What might be more telling is evidence of processed materials. manufactured alloys with specific ratios, synthetic compounds not found in nature, organized structures within the debris that suggest assembly rather than accretion. These would be harder to explain through natural processes. There is also the question of behavior. Natural comets are passive. They respond to solar heating, gravity, and radiation pressure in predictable ways. They do not make decisions. They do not adjust their trajectories. They do not exhibit purposeful action. If 3I-ATLAS were artificial, if it contained active systems still functioning after billions of years of travel, those systems might reveal themselves through behavior. Any change in trajectory that cannot be explained by known forces would be extraordinarily significant. A sudden acceleration or deceleration, a course adjustment that moves the object toward or away from Earth, an increase or decrease in rotation rate. These would suggest agency rather than physics, intention rather than circumstance. They would suggest that something aboard 3I-ATLAS is aware and active and making choices. Loeb has been careful to emphasize that he does not expect such behavior. The most likely explanation remains that 3I-ATLAS is a natural comet, strange but natural. The anomalies have conventional explanations, even if those explanations are incomplete or unsatisfying. The scientific community is right to maintain skepticism. Extraordinary claims require extraordinary evidence, and so far the evidence is suggestive rather than conclusive. But December 19th represents something like a deadline. As 3I-ATLAS recedes from both the Sun and Earth, observation becomes progressively more difficult. The object dims, the angular resolution decreases, the window for gathering high-quality data closes. Whatever we learn in the coming weeks will shape our understanding of this visitor for decades to come. Missed opportunities will not return. The solar eruption that occurred in recent days adds another variable, an X-1.9 flare, powerful enough to send shockwaves across the Sun's surface and destabilize nearby magnetic structures. The active region responsible will rotate into Earth-facing position just as 3I-ATLAS reaches closest approach. Enhanced solar wind speeds, elevated radiation levels, and magnetic disturbances will all affect conditions in the inner solar system. How this might influence 3I-ATLAS is unclear. A natural comet would experience increased interaction between solar wind and its ion tail. The charged particles streaming from the Sun would push more strongly on the ionized gases surrounding the nucleus. This might enhance visible activity, making the comet appear brighter and more dynamic during the observation window. Or it might complicate observations, adding noise to data that scientists are trying to interpret. If 3I-ATLAS carries any active systems sensitive to electromagnetic disturbances, a major solar storm could have effects we cannot predict. Shielding designed for interstellar conditions might not be optimized for intense solar activity. Communication systems might experience interference. Navigation systems might receive corrupted signals. We are speculating here, of course. There is no evidence that 3I-ATLAS has active systems, but the timing of the solar eruption, arriving just as the object enters peak observation position, adds a layer of unpredictability to an already uncertain situation. Amateur astronomers will play a significant role in the December 19th observations. Professional telescopes have limited time. Observation schedules are packed. Priority is given to the highest impact science, but amateurs can observe for hours at a time, building up exposure and tracking changes that might happen on timescales too slow for snapshot imaging. The community that has gathered around 3I-ATLAS is remarkable. Photographers from Germany, Japan, Spain, Australia, and dozens of other countries have contributed images. Online forums share processing techniques and observational strategies. Discoveries that would once have taken months to percolate through academic channels now spread in hours. If something unusual happens on December 19th, the world will know almost immediately. There is also the question of what does not get released. NASA withheld Mars Reconnaissance Orbiter images of 3I-ATLAS for over a month, citing the government shutdown and other administrative reasons. Loeb publicly criticized this delay, arguing that transparency in scientific discovery should be paramount. The images were eventually released and showed what appeared to be a standard cometary nucleus. But the delay fed speculation about what might have been in those images and why the agency was reluctant to share them. December the 19th will test whether this pattern continues. If observations reveal something truly anomalous, will that information be shared promptly with the public? Or will there be delays, deliberations, concerns about how such news might be received. The scientific community generally favours openness, but governments and institutions sometimes have other priorities. The history of unusual phenomena is filled with cases where information was suppressed, delayed, or dismissed in ways that later proved counterproductive. I do not know what December 19th will reveal. No one does. The object could behave exactly as a natural comet should, and the mystery could recede into the background noise of ordinary astronomy. Or the observations could produce new anomalies, new questions, new reasons to take seriously possibilities we currently treat as speculation. The universe does not arrange itself for our convenience. It shows us what it shows us, and our job is to look carefully and think honestly about what we see. 3I-ATLAS entered our solar system from the direction of the constellation Crater. It will exit toward the constellation Virgo. Its passage has taken less than a year from the perspective of Earth observers, but that passage spans distances beyond imagination and origins beyond knowledge. Whatever it is, wherever it came from, whoever or whatever might be associated with it, December 19th is our best chance to learn more. The countdown continues. What the silence means. The Meerkat radio telescope in South Africa pointed its dishes at 3I-ATLAS on November 5th, 2025. 64 antennas, each 13.5 meters in diameter, working together as a single instrument of extraordinary sensitivity. They searched for narrowband radio transmission, the kind of signal that would indicate technological origin, a beacon, a communication attempt, any electromagnetic whisper suggesting that something aboard the interstellar visitor was trying to reach out. They found nothing. The first limit on technological radio transmission from 3I-ATLAS came back negative. No artificial signals were detected within the frequencies and power levels the search could probe. This was not surprising. It was not even disappointing, really. SETI searches almost always return null results. The universe is vast and quiet, at least in the ways we know how to listen. But the silence raises questions that are worth exploring. If 3I-ATLAS were artificial, if it carried intelligence of any kind, why would it not transmit? Why would it pass through a solar system containing a technological civilization without attempting communication? What does the silence mean? One interpretation is the simplest. 3I-ATLAS is natural. It is exactly what mainstream science claims it is, an unusual comet from another stellar system, chemically strange and behaviorally anomalous, but fundamentally just a ball of rock and ice following the laws of physics. There is no signal because there is no intelligence to generate one. The silence means nothing more than the absence of a transmitter. This interpretation fits the data. It requires no exotic assumptions. It aligns with the scientific consensus. If forced to bet, any reasonable person would put their money on this explanation. Occam's razor favours the natural hypothesis, and we should respect that principle even while exploring alternatives. But let us consider other interpretations. If 3I-ATLAS is artificial, why might it remain silent? The first possibility is damage. 10 billion years is a long time. No technology we can imagine would function perfectly across such a span. Components fail, systems degrade, radiation damages circuits, micrometeorite impacts erode surfaces. An interstellar vessel that began its journey with powerful transmitters might arrive at its destination with those transmitters non-functional. The will to communicate might exist, the capability might not. The second possibility is intentional stealth. Not all visitors announce themselves. A reconnaissance mission observing an unknown civilization might choose to remain hidden, gathering data without revealing its presence. From the perspective of such a mission, broadcasting radio signals would be counterproductive. It would alert the natives. It would invite investigation. It would potentially provoke reactions that could compromise the mission's objectives. The dark forest theory, proposed as a solution to the Fermi paradox, suggests that advanced civilizations remain silent because the universe is dangerous. Any civilization that broadcasts its presence risks attracting predators. The logical response is to stay quiet, observe without being observed, and eliminate potential threats before they become actual threats. If 3I-ATLAS operates according to this logic, its silence is not absence but strategy. The third possibility is incompatibility. We searched for narrowband radio signals because that is what we know, how to detect. Human technology uses radio for communication across distances. We assume any technological civilization would do the same. But this assumption might be wrong. A civilization millions of years more advanced than ours might have abandoned radio long ago. They might communicate through gravity waves, quantum entanglement, neutrino beams, or methods we have not discovered yet. They might consider radio as primitive as we consider smoke signals. Their transmissions might pass through our solar system constantly, undetected because we lack the instruments to perceive them. The silence at radio frequencies does not prove silence at all frequencies. It proves only that we did not detect what we were looking for. What we were looking for might be the wrong thing entirely. The fourth possibility is patience. Communication requires timing. A message sent too early might be intercepted by civilizations that no longer exist by the time a response could arrive. A message sent too late might miss its intended recipient. An intelligence operating on timescales of millions of years would think about communication very differently than we do. 3I-ATLAS passed closest to Mars in early October. It will pass closest to Earth in mid-December. It will pass closest to Jupiter in March of next year. Each of these encounters might be an opportunity for observation rather than communication. The silence now does not preclude contact later. Perhaps the vessel is waiting, gathering data, assessing whether communication would be wise. The fifth possibility is perhaps the most unsettling. What if 3I-ATLAS has already communicated and we simply did not recognize it? Reports emerged in late October of a mysterious pulse sequence detected at 1420 MHz, the hydrogen line frequency associated with SETI protocols. The sequence allegedly followed a Fibonacci pattern, 8, 13, 8, 5, 13, 8. Interpretations range from cosmic noise to deliberate message. Most scientists dismissed the reports as artifacts or hoaxes. No peer-reviewed confirmation appeared. But the story persists in fringe communities. The pattern is said to encode a message. Observe, prepare, understand, the gate awaits. This sounds like fiction, and it probably is. But it illustrates something important about how communication might fail. A message from an alien intelligence might not look like a message to us. It might be embedded in patterns we dismiss as noise. It might use encodings we do not recognize. It might require context we do not have. If 3I-ATLAS transmitted information in the structure of its jets, the timing of its brightness variations, the distribution of its swarm, we might observe these things without understanding they were communications. We might catalogue them as anomalies, publish papers about them, debate their natural explanations, all while missing the message entirely. This is humbling. We like to think of ourselves as intelligent, capable, advanced. And in some ways we are. We have sent probes to other planets. We have decoded the structure of DNA. We have built global communication networks and artificial intelligences. But compared to a civilization millions of years older than ours, we are infants. Our technology is primitive. Our science is incomplete. Our understanding is fragmentary. The silence of 3I-ATLAS might simply mean that we're not ready to hear what it has to say. Not technologically unready, though that might be true too. Conceptually unready, philosophically unready, unable to recognize communication because we cannot yet imagine what form it might take. There is one more interpretation of the silence that deserves consideration. Perhaps 3I-ATLAS is listening rather than speaking. A vessel on a reconnaissance mission would prioritize gathering information over transmitting it. Every radio emission is a beacon that reveals your position. A stealthy observer would maintain radio silence, using passive sensors to collect data while revealing nothing about its own presence or capabilities. From this perspective, the silence is not emptiness but attention. 3I-ATLAS is paying attention to us. It is recording our radio emissions, our radar pulses, our satellite communications. It is watching how we respond to its presence. It is learning about us in ways we cannot learn about it. This is the asymmetry of first contact. Whoever speaks first reveals themselves. Whoever listens first learns about the other. 3I-ATLAS, if it is intelligent, has been listening for months. It knows we have detected it. It knows we're tracking it. It knows we're speculating about its nature. It knows everything we have broadcast and quite a bit we have only thought. We know almost nothing in return. The chemical composition of its outer layers, the rough dimensions of its trajectory, the anomalies in its behavior that we cannot yet explain. Against the vast knowledge gap, our instruments seem feeble and our science inadequate. December 19th will not close this gap. Even the best observations will only scratch the surface of what 3I-ATLAS might be. The silence will likely continue. The questions will remain unanswered. And we will be left where we have always been, a young civilization on a small planet, looking up at the stars and wondering who else might be looking back. But there is dignity in wondering. There is value in asking questions, even when answers are not forthcoming. The silence of 3I-ATLAS challenges us to think harder, observe more carefully, and imagine more boldly. It reminds us that the universe is under no obligation to make sense to us. It owes us no explanations. It sends us no guidance. We must find our own way, build our own understanding, and accept that some mysteries may never be solved. The silence means whatever we need it to mean. For some, it is reassurance that we are alone, that the cosmos is empty and safe. For others, it is challenge, a dare to develop the capabilities we need to truly listen. For still others, it is invitation, a door standing open to possibilities we can barely imagine. Whatever 3I-ATLAS is, its silence has already changed us. We have looked at something from beyond our solar system and recognized that we do not understand it. That recognition is the beginning of wisdom. The question we cannot answer. We have traveled far tonight, from the swarm hypothesis to the anatomy of motherships, from the engineering of interstellar arcs to the frozen passengers who might inhabit them, from alternative biochemistries to the trillion fragment problem, from the anticipation of December 19th to the meaning of cosmic silence. Each topic has opened new questions while closing few. Each speculation has led to further speculation. This is the nature of genuine mystery. It does not resolve neatly. It expands. And now we face the question we cannot answer, the question that underlies everything we have discussed, the question that will remain unanswered long after 3I-ATLAS has vanished into the interstellar dark, heading toward Virgo, leaving our solar system forever. Is 3I-ATLAS natural or artificial? I want to be clear about something. The evidence we have does not support a definitive answer. Mainstream science interprets the observations as consistent with an unusual but natural comet. The carbon dioxide-rich composition suggests formation in a cold, carbon-rich stellar environment. The metal-rich emissions could reflect the chemical makeup of whatever disk produced the object billions of years ago. The anti-tail, the jets, the swarm if it exists, all of these have potential natural explanations, even if those explanations are incomplete. A.V. Loeb's 12 anomalies are provocative but not conclusive. Statistical unlikelihoods are not proof of design. Strange coincidences happen in a universe vast enough to contain every possible configuration of matter and energy. The trajectory aligned with the ecliptic could be chance. The timing that brought 3I-ATLAS close to multiple planets while hiding it from Earth during perihelion could be chance. The unusual chemistry could be chance. And yet, the accumulation of anomalies creates a pattern, not proof, but a pattern that reasonable people can interpret differently. If you believe the universe is purely natural, purely random, purely indifferent to observers, then every anomaly has a natural explanation waiting to be discovered. Your job is to find those explanations and add them to the great edifice of science. If you believe that technological civilizations might exist elsewhere in the cosmos, that some of them might be millions or billions of years older than ours, that they might send probes or vessels or messages across interstellar distances, then the anomalies become hints, clues, suggestions that perhaps this time, this object, this visitor might be different. Neither belief is irrational. Neither is provable given current evidence. We are stuck in the uncomfortable middle ground where multiple interpretations are consistent with the data. This is not a failure of science. It is science working as it should, maintaining appropriate uncertainty in the face of insufficient information. What we know for certain is limited. 3I-ATLAS originated outside our solar system. Its trajectory is hyperbolic, meaning it will never return. It is large by interstellar object standards, possibly several kilometers in diameter. It has unusual chemical signatures compared to solar system comets. It exhibited a sunward anti-tail that defies simple explanation. It passed through perihelion without fragmenting completely. It is now receding, heading toward its December 19th close approach with Earth, before continuing outward past Jupiter and eventually beyond any telescope's reach. What we suspect but cannot prove is vast. The swarm of fragments that might surround it, the passengers that might be frozen within, the intelligence that might have designed it, the purpose that might guide it. Each of these suspicions opens onto endless speculation, none of which can be confirmed or denied with the instruments we possess. This is perhaps the deepest lesson of 3I-ATLAS. We are limited. Our technology is limited. Our understanding is limited. We look at something from another star system, something that has been travelling for longer than our planet has existed, and we cannot determine what it is. We have theories. We have data. We have computers and telescopes and generations of accumulated scientific knowledge. And still, we cannot answer the most basic question. Is it natural or made? There is humility in this admission. We are not the measure of all things. The universe is not scaled to our comprehension. Mysteries exist that we may never solve, not because they are unsolvable in principle, but because we lack the tools and the time to solve them. But there is also wonder. The same uncertainty that frustrates our desire for answers feeds our sense of possibility. If we knew for certain that 3I-ATLAS was just a comet, the story would be interesting but contained. A data point in the catalogue of interstellar objects, a footnote in the history of astronomy. Because we do not know, because we cannot know, the story remains open. The possibilities remain alive. The universe remains stranger and more wonderful than any single explanation could capture. I think about the people who will be watching on December 19th, the professional astronomers at their consoles, adjusting instruments, recording data, hoping for that one observation that might tip the balance toward clarity. The amateur observers in their backyards, cold fingers on telescope controls, eyes straining at eyepieces, participating in a moment of cosmic significance. The curious, public following along through news reports and social media, sharing in the collective wonder of a species confronting the unknown. We are all part of this. Every person who has wondered about 3I-ATLAS, asked questions about it, read articles or watched videos or simply looked up at the night sky knowing something strange is passing through. We are a civilization awakening to the possibility that we are not alone, not because we have proof, but because we have encountered something that reminds us of how vast the cosmos is and how little we understand it. If 3I-ATLAS is natural, it teaches us that the universe produces wonders beyond our experience. Objects from other stellar systems carry chemical signatures we have never seen. Interstellar space is not empty, but filled with travellers we're only beginning to detect. Our solar system is not isolated, but visited by emissaries from the galactic population of debris and wanderers. If 3I-ATLAS is artificial, it teaches us something even more profound. We are not the first, we are not the only. Intelligence arises elsewhere, and does things we can barely imagine. Civilizations build vessels that last billions of years and send them across unthinkable distances for purposes we may never understand. The universe is not just vast but inhabited, not just old but experienced. Either lesson is worth learning, either expands our sense of what is possible, either changes how we think about ourselves and our place in the cosmos. I want to thank you for staying with me through this exploration. We have covered speculative territory tonight. Motherships and frozen passengers and alternative biochemistries. These are not mainstream scientific topics. They are thought experiments, imaginative exercises, ways of stretching our minds to encompass possibilities we would otherwise dismiss. If you found value in that stretching, if you enjoyed the journey even without arriving at a destination, then this time was well spent. Remember to like this video if you have not already. That simple action tells the algorithm that content like this matters to you. And if you are not yet subscribed, consider joining our community of curious minds. We explore topics like this regularly, combining scientific rigor with speculative imagination, trying to see the universe not just as it is, but as it might be. A brief note on what we have discussed. This video contains speculation about topics that remain scientifically unresolved. The swarm hypothesis is one interpretation of observations that have other possible explanations. The mothership concept is theoretical and not supported by confirmed evidence. Alternative biochemistries remain speculative extrapolations from limited data. None of what we have discussed should be taken as established fact. The purpose is to explore possibilities, not to claim certainties. And now, as December 19th approaches, I invite you to join in the watching. Point your telescopes at the sky if you have them. Follow the news reports if you do not. Be part of this moment when humanity, for the third time in its history, observe something from beyond our solar system passing through our cosmic neighborhood. What will we find? I do not know. Perhaps nothing more than a strange comet behaving in ways we will eventually explain. Perhaps something that deepens the mystery further. Perhaps, just perhaps, something that changes everything. We think we know about our place in the universe. The stars are old. The galaxy is vast. Time stretches in both directions beyond comprehension. And somewhere out there, moving through the darkness between suns, travellers are passing. Some are rock and ice, fragments of stellar nurseries scattered across the void. Some might be more. We look for them with the best tools we have. We wonder about them with the best minds we have. And we wait, patient and curious, for the answers that may never come. Good night, wherever you are. Whatever time zone holds you, whatever questions keep you awake. We share this moment together, billions of humans on a small blue world, watching something ancient drift past our door. We may never know what it is, but we will never stop wondering. And that wondering, that refusal to accept ignorance as final, that insistence on looking and asking and imagining, that is what makes us human. That is what will someday perhaps make us ready to meet whatever else is out there. Sleep well, dream of distant stars, and remember that the universe is far stranger, far more wonderful and far more mysterious than any of us can imagine.